gap again, right? But ND and NA, they are the same. So basically the numbers are going to be the same, right? So now we figure out this one. I think we're done. Now we can go back to that equation order. Let's start with lambda A. Let's replace them there. So it's going to be this. I'm going to put it here. This value, right? It's going to be LAA0 plus LALIA. And this machine, remember, is a three-phase system symmetrical. What does it mean symmetrical? IA plus IB plus IC, 0, because I'm going to use that thing a little bit later. Plus. It's going to be LABIB. How much is LABIB? Yeah, right? So minus basically half of LAA0 IB minus half of LA0 IC. And what was the last one? LAF. Yeah. Right, I'm going to put this one. Plus LAF cosine theta times IF. Right? Let's look at this one. I'm going to simplify it. Let's factor in 1 over 2 LAA0 is going to be IB plus IC. How much is IB plus IC? Minus IA, right? So let's write it down again. As I say, this part is not in your book. You know, it jumped to, after all we go through this thing, I'm going to come up with a circuit. It jumped to that circuit. So this is the equivalent circuit of the machine. Now, lambda A is going to be LAA0 plus LALIA. So basically, minus times minus is going to be positive. It's going to be half of LAAIA, right? And I'm going to write it out. So basically, lambda A is going to be 3 over 2 LAA0 plus LALIA plus LAF cosine theta I. You are almost there. So here, what I'm calculating here, I'm calculating the back EMF generated in these windings, right? Now, if you think about it, look at here, this winding, this one, let's say connected, for example, a source. These three here, they are connected to a source, right? They are connected to a source, right? Current IA going here, current IB is going here, current IC is going here, right? What's the equation for this one? We can say, let's call this one V terminal. Let's call this one V terminal. I'm going to write it for phase A. So we say V terminal A is equal to RA, for the small, RAIA, right? RA is the resistance of this winding, right? RAIA, right? Plus what? Right? How much voltage I have induced here? Go back again to the transformer. If you don't follow this one, go back to this one. See how simple was this one. We said, let's say we have a back EMF, we generate E here, right? This one was a V, right? And this winding is going to be R, right? This current is I. We say V is equal to Ri plus E, right? How much was E? If this one C, this one was N, right? We say E is equal to d lambda over dt, right? Or N dV over dt, right? I'm doing exactly the same thing here. I'm doing exactly the same thing here. It says V is equal R plus d lambda over dt, right? Now I have my lambda here. I'm going to go take a derivative of this one. So basically, if I do that one, now I can draw my circuit. I can come up with one circuit for the system. So I need to calculate the d lambda over dt. Let me see, I make sure I cover everything. Oh, we call this one lambda AF. Let's call this one for now lambda AF. So basically it's gonna be right. This is the dimension of this one is a lambda, right? Because on this side is lambda, this one is lambda, right? Now let's calculate. I need to calculate what d lambda a over dt, right? Let's calculate out. D lambda a over dt is going to be this. This is a constant number, right? Times dia over dt. So it's going to be 3 over 2 LAA0 plus LAL dia over dt plus d lambda AF over dt, right? So this is like an inductor, right? This is like an inductor, LDI over dt, right? Which the value of inductance is this much, right? Let's work on this step, d lambda AF over dt. We define LS, synchronous inductance. We call it synchronous inductance. We define that one as this number. This one is always given. For a machine, usually this one is given. If you look at into the data machine, they say the synchronous inductance of machine is this much, the number. So let's define that one LS. Now I'm going to work on the E, and let's define this one EAF. Also, we define this one EAF. We're going to go calculate the EAF. So basically, we get to this point. With this definition, we said VT, I'm not putting A because it's a phasing, by default is phasing, is equal to RA IA plus LS DIA over DT plus EAF. Right? EAF. If I want to put it in the phasors, how is it going to be? If I put this one in the phasors, it's going to be VT is equal to RAIA plus what? Plus what? J omega LS IA, and let's show this one with EAF. Right? The phasor of that one, right? So how much is this? We call it XS, synchronous impedance of the machine. XS, synchronous impedance of the machine. So basically, VT is going to be RAIA plus JXS IA plus EAF. And still, I haven't calculated this one. I need to calculate this one, but let's leave it for a little bit later. So I'm going to draw a circuit to show this one. This is phase A. We can draw the same thing for phase B. Phase B, the only thing is going to be R, again, right. Phase B is going to be RB, IB plus JXS. JXS is the same. IB plus EBF, right? Phase C is going to be RC, IC plus JXS, IC plus ECF. But RA, RB, and RC, they are all the same. We call it R. Let's call it R. These are the same binding. They have the same resistance. Let's say RA is equal to RB equal to RC, let's call it R. Let's give it a name, R. Because the three windings, they are exactly the same, right? The resistance of all three windings, they are the same. Now I can draw my circuit. My circuit is going to be like this. Right here. Isn't this correct? That's that equation I put in the circuit, right? I put that equation in this circuit. I showed you in this circuit. Very simple, you know. There is a resistance for the phase winding. There is a not exactly impedance of the winding. You can see the impedance is pretty complicated because here we went through all this crap here to get here. I don't want you to do. I want you how I get there. Well, I don't expect you to go through this thing for exam. Forget it. You don't learn about this one. But if you know how to get here, if you go to the book, it starts from here. So this is the circuit of this machine. But now you know what's XS. You know how we got to the XS. You know, there are a lot of story behind this one to get to the XS, right? So this is the equivalent circuit of one phase of synchronous machine. This is a motor. You know what I draw here? It was a motor, right? If you want generator, the current is only that way, right? So basically, you can assume this one will be 0. Okay, now EAF. Let's work on EAF. You know, before giving it the number to this one, let's start to work on EAF. Was EAF somewhere behind here. The lambda AF, right, and lambda AF was this one, right? Let's go back here. Lambda AF, it was LAF cosine theta IF, right? So let's calculate the EAF. So it's going to be this one, you need to take a derivative of this one, right? It's going to be let's take a derivative of this one. It's going to be LAF is a constant number. This one is going to give me omega, right? Or no? No. Yes, sorry. You get omega cosine theta. This IF is a DC current. This IF is a DC current. You don't have a magnet, right? I put a DC current here, it's going to give you a magnet, and I'm rotating this magnet. So basically, if you are going to write here, it's going to be LAF, derivative of this one times this, plus this one times derivative of this one over dt, right? How much is the DIF over dt? Is 0, right? Basically, if you take a derivative of this one, LIF is constant, take it out. It's going to be this one times derivative of this one, right? Which is 0, forget that one. Plus this one times derivative of this one, no? Write it here. IF, let's show it this way, means it's a DC current. When you put it this way, means a DC current. This is not phasor, this is a DC current. Because I'm showing you the capital, letters. So basically, it's going to be LAF omega IF cosine theta. How much is this one? See, I put it in the phasors, right? I showed it with EAF, right? Right? How much is that number? How much is that number? Right? When we do the phasors, usually we use the RMS value, right? This is the RMS value of input voltage. This is the RMS value of the current. This is the RMS value of EAF, right? If the magnitude is that much, right? If the magnitude is this much, right? So this one is the, how much? EAF is the RMS value of that. So basically, EAF over square root of 2 is equal to omega LAF IF, or you can say EAF. If you put square root and for omega equal to 2 pi f, right? So you are going to get to this number, 4.44 LAF IF times f. Times f. Because omega is a 2 pi f, right? 2 pi times square root of 2. So it's, oh, sorry. I mean, this one divided by square root of 2. Right? This is the magnitude. And this is 1. This is the square root of 2. EAF, right? That's that. So basically, EAF is this one divided by square root of 2, right? 2 pi divided by square root of 2, 4.44 times F times LAF times IF. So I think we are good here now. I'm not gonna. Yeah, we have to stop. We are good here. So we covered the most difficult part. The rest is going to be the calculation. You know, this one was the conceptual part. So we get to this one. We got the equivalent circuit of the machine here. Next class, I'm going to take it from here. And next class is basically going to be your book. If we're going to start to go through the book.
It's like cosine theta, or
cosine theta is staying here.
oh, okay.
Right?
So you want to do it in the phases? Oh, of course.
Yeah, we want to go theta, right? Omega 2. So there's no class March 1st. You don't remember, no class March 1st. The homework from now on, every Thursday. We have already number 3, number 4, and number 5 is going to come, but due Thursday, you know.
Alright, I'll be here to change the if you know it says 2800 voltage, they change the 10 on the machine. Let's go. I really do the work now, I gotta go. I guess everyone's
Oh, I saw it on this side. Yeah, dude, it's not like that.
Mine's time change.
When they set all that